In this video and the additional example problems, we're going to be discussing Chapter 3 in the Hibbler textbook, which is particle equilibrium. In mechanics terms, a particle has negligible dimensions. And so you can think of it as a point, but it can be a ring, it can be a body, it could be a body that looks like this. We have a problem that we work a little bit later on that's basically like a drum in a forklift or in a cradle. And there's a force here, there's a force here, and then there's a center of gravity at the center. And all of these forces intersect at this point, which is the mass center. And so if you have forces that intersect at a point, that's called a concurrent force system. So the body itself doesn't have to be a point or a particle, but the force system that acts on it has to intersect at a point. In other words, it has to be a concurrent force system. We'll draw these cable problems that will look like this. You have a mass hanging here, and a horizontal cable here, and a cable here. We'll draw this guy as a point, but he may really be a ring if you look at it up close. Or he might be some other device. But my point is, it may not necessarily be a point. It could be a ring, it could be a drum. But basically, if you write forces along these cables, then the line of action of these forces all intersect at a point that's in the center of that ring, which makes it a concurrent force system, which I find an odd term, because to me concurrent implies things that act at the same time. But in mechanics lingo, concurrent means they intersect at the same point. And so this is a concurrent force system. This is a concurrent force system. When you get to dynamics, there's times where we'll take an automobile problem or a motorcycle problem and treat it as a real body. Treat it if this is a motorcycle. And you've got a reaction here, and a weight here. There's times where we'll treat this guy as a rigid body. But on the other hand, there's times where you're dealing with like a motorcycle jump, where we might treat that motorcycle as a particle as it moves along that path. And so a particle versus a rigid body are idealizations that we use in mechanics, both in statics and dynamics, when we're modeling physical systems anyway. But chapter 3 is about particle equilibrium, or point equilibrium, where there's a concurrent force system acting. And if there is a concurrent force system, and we talk about equilibrium of that particle, the conditions for static equilibrium are basically that the sum of the force vectors is equal to 0. In our previous chapter, we sometimes had several forces acting. Here's a ring, maybe. And we had several forces acting on that ring, and we would sum those forces to some resultant. We would replace this guy with a single resultant force acting at some angle. That's a resultant problem. But for equilibrium to occur, this resultant has to be 0. Newton's first law says that the body in motion will remain in motion, or body at rest will remain at rest, unless an unbalanced force acts on it. And so statics is all about balanced forces. In other words, that the vector sum of all the forces that act on a body equals 0. Now the body may or may not be stationary. the body actually could be moving at a constant velocity. So in other words, it has a zero acceleration, and it will still be in force equilibrium, and you could argue static equilibrium, where the sum of the forces is equal to zero. And so that's still static equilibrium. Occasionally there's a test problem, a simple conceptual problem might say a body moves at a constant velocity. And well, it will if the acceleration is zero, and if the summation of forces is equal to ma and acceleration is equal to zero, then the summation of forces is equal to zero. So just pay attention to that on an exam. But again, this chapter is about particles, and it's about equilibrium. And so the equilibrium conditions, you can write a vector equation where the sum of the vectors is equal to zero. But more commonly, for a 2D problem, we will write the scalar equations, where we sum forces in the x direction is equal to zero, we sum forces in the y direction is equal to zero, and then these are our scalar equations or conditions for equilibrium. For a 3D problem, we'll write three scalar equations in the x, y, z directions. One of the things that you'll learn for a 2D problem especially is obviously most often we're going to write equations in the standard x and y coordinate systems. But I'll actually show you a couple of examples where it's useful to create a rotated coordinate system, an x prime and a y prime, that works better for a particular problem or simplifies a particular problem. So one of the tricks that an excellent static student understands is that at times, if you create a rotated coordinate system, you can simplify a problem. One more thing about these conditions for equilibrium, because there's two equations in 2D, that means when I have a 2D problem, I can write two equations. But if I have three unknowns or four unknowns, and I just have two equations, then the problem becomes statically indeterminate. In other words, I've got more unknowns than I have equations, and I can't solve it. The same is true in 3D. If you have more than three unknowns, if you have 4 cables or 5 cables supporting, for example, in 2D, if I have a weight here, which I know, a cable here, a cable here, so there's an unknown here, there's an unknown here, this is 100 pounds. I have two unknowns. I can sum forces in the x and sum forces in the y to get these two unknowns. But if there is a third cable here with a third force, or maybe a fourth cable with another force, now I have 4 unknowns. And if I sum forces in the x and y, I just have 2 equations. And I'm in trouble. This problem with multiple cables is static, or with more cables than 2, is statically indeterminate. Whereas if it's just 2 cables matching my 2 equations, it's statically determinate. And so later in this class, we're going to talk about static determinacy and indeterminacy later as we go. One of the interesting things about this chapter, this particle equilibrium chapter, is that at face value, it's a simple chapter. It's just particles, simple equations of equilibrium. But there's actually a lot of subtle principles that we'll learn in this chapter that we'll apply later. I was thinking the other day that, there's a book, Everything I Needed to Know as an Adult I Learned in Kindergarten. And you could argue that everything I need to learn in statics I learned in the particle equilibrium chapter. It's a pretty simple chapter, but there's some subtle things in the chapter that are useful that will carry on to later chapters, that if you learn them now and invest the time to learn them now, it will build a foundation for you that will help you in future chapters. But again, the idea of statically determinate problems or statically indeterminate is something you need to understand. So these are my conditions for equilibrium. In 2D and 3D, we usually write the scalar equations. So just kind of contrasting these things, right now we're in chapter 3, which is particle equilibrium, negligible dimensions, concurrent force system, conditions for equilibrium, we're just summing forces is equal to 0. And if we draw a picture, which is basically called a free body diagram, free body diagram, which I abbreviate FBD. The free body diagram is a simplification of our picture on which I note the unknowns, the knowns, their directions. I label them, and based on my free body diagram, I write these equations. The free body, this is another lesson that you learn in chapter 3 that you have to do throughout the rest of statics, and that is draw a free body diagram. Super important. So this is chapter 3, particle equilibrium. 2 chapters from now, chapter 5 in the Hibbler textbook, we're going to do rigid body equilibrium. And now instead of a point, you now have a body with some dimensions to it, either in 2D or 3D. The force system acts at different points on that body. And so in general, that force system is not concurrent. In other words, if you move these forces along their lines of action, they don't all intersect at a point. So it's not a concurrent force system. And so now the conditions for equilibrium for this guy is that the sum of the forces needs to be 0, but also the sum of the moments need to be 0. So in other words, the turning effect of all of these forces. So if you sum moments about a point P here, which next chapter we're going to learn about moments, but you've already learned about moments or torques in physics. But the turning effect of these forces on a body, those guys have to sum to 0 as well for static equilibrium. But again, for this chapter, we're just going to do forces, but soon we'll do forces and moment equilibrium. So talking more about the free body diagram, super important. You must learn to draw free body diagrams. So what we're going to do is we're going to isolate the particle from its surroundings. In other words, and basically we're looking for the point at which these forces are concurrent. And so that's our point that we're going to draw. We're going to indicate all the forces, cables, weights, any constraints or supports that might be occurring. We'll label those forces. If there's cables, we will always label them in tension, TAB, TBC. Some of the problems we'll look at will have a solid member or a strut. And so a solid strut can be either in tension or compression. In other words, it can pull or it can push. And so for a solid member, I will usually call it FCD or FDE, where T implies tension, F is just more of a generic force term. And so that's my preference. Again, as you draw this force, you can draw it pushing on if a member pushes on a particle, then the particle pushes on. Newton's third law says that for every force, there's an equal and opposite force. Or for every action, there's an equal and opposite reaction. And so if you're looking at a strut and a pin here, and some forces acting at this pin, if I draw a free body diagram of that pin, I can draw the strut pushing on that pin. And if I draw the free body diagram of the strut, then the pin is pushing on the strut. And so if the strut is pushing or the pin is pushing, then that puts this stress this strut in compression. On the other hand, if this strut or a cable is pulling on the pin with a tension force, then that means that the pin is pulling on the strut. And so if the pin is pulling on the strut, then the strut is in tension, or this cable is in tension. So compression is pushing, the strut pushing on the pin, or the pin pushing on the strut, or tension is pulling, the strut pulling, or the strut or cable pulling on the pin, or the pin pulling on the strut or the cable. Pushing and pulling. Finally, some of these problems will have springs on them. And a spring, as you know, as you stretch the spring, a linear spring will exert a force. This is a linear spring. Linear spring. Usually, the force developed by the spring is a straight line relationship between the stretch of the spring with the slope of K. It's a linear spring. There's also nonlinear springs, but in this class, we'll usually just consider a linear spring. And so basically, we'll say F is equal to Ks. But this stretch is equal to the original, well, it's equal to the current length of the spring minus the unstretched length of the spring. And so we can also write F is equal to K L minus L naught. So this is a spring with an original length L. With an original length L naught. But then if we stretch that spring to some new position where this is L, the difference in these two, L minus L naught, is stretch. That's a spring equation that we will use. And this linear relationship here is called Hooke's law, as you know. The spring constant is usually in force per length, so newtons per meter, pounds per foot, something like that. And the lengths are usually in meters or centimeters or feet or something like that. So this is an introduction to particle equilibrium. Next, we're going to work a number of two-dimensional problems to illustrate these principles. Then we're going to work a number of three-dimensional problems to illustrate these principles, and we'll work some spring problems as well. So as I work the problems, you'll see these illustrated over and over and over again.